Okay, I think we can officially start our webinar. Welcome everybody. I am pleased to welcome you to the third and final webinar of the OVERLEAF project series. Today we will explore some of the latest advancements in the development of the low pressure liquid hydrogen storage system that we are developing in OVERLEAF, with a specific focus on its inner tank. The session brings together 4 experts, each of them partner of the OVERLEAF project. Those experts will share their research on materials, manufacturing processes, and testing methodologies for the inner tank. All of these are essential for ensuring high performance of the cryogenic resistant tank components. We will start with Teddy Fournier from Canoe, who will introduce innovation in 3D filament manufacturing, followed by Ander Raizabal from IMEN, who will present large format additive manufacturing strategies, both key aspects for producing full-scale hydrogen tanks capable of withstanding extreme cryogenic conditions. Then we will have Jordi Renard speaking from the University of Girona, who will discuss mechanical testing methodologies for 3D printed materials at cryogenic temperatures. And lastly, we will have Ionete Eusebilarian from ICSI, who will address an important challenge in hydrogen cryogenic environments, which is the removal of trapped gases from open cell foams, providing insights into experimental procedures and key findings, specifically on gas purification techniques. At the end of the session, we will also have a 10 minutes question and answer window. So please feel free to submit your questions in the chat during the webinar, and we will make sure to address them in the final discussion. One final remark before starting. Do not forget to follow the OVERLEAF project on social media. You can find us both in LinkedIn and Blue Sky. Since we are at the final stage of our project, which is closing in October, we will therefore soon release everything we've been working on the past years, so make sure you won't miss it. With no further ado, I'll leave the floor to Teddy, which is our first speaker. I will give you the control of the presentation right now.
Okay, it's working.
Thank you, Teddy.
Hi, everyone. So I'm gonna start this session. Okay, it's working. So during the OVERLEAF project, Canoe works on the 3D filament manufacturing, and I'm gonna explain how we make it. So I just want to notice that the real workers behind this work is Arthur Biss from Canoe in Pau. Benjamin Ries also worked on some tasks of this project, but he is not here today. And myself, I'm today your webinar speakers. So in the OVERLEAF project, in this webinar, we talk about the inner tank. The inner tank, this is the pink parts in this picture. So this is the part where the liquid hydrogen will be stored at very low temperature, about 20 K. And the size of this spherical object is pretty impressive because it's about 1.5 meters diameter. So that means it represents a lot of materials to produce, and especially for 3D printing. It's something like more than 35 kilograms of filament spool that we have to manufacture. So before to manufacture such quantity of materials, we need to develop it. And the development of such materials was done thanks to different type of materials provided by Arkema. So we work on one side with renewable materials. It's a renewable polymer called polyamide 11. It's mainly made from renewable resources like castor oil. And so we work with 2 different grades of polyamide 11. And this grade of materials are pretty common, but they get some difference, like you can see in the remarks. The first one show excellent adhesion between the layers during the printing process, which is a pretty good thing. And for the second one, got a specific kinetic during the crystallizations. And you have to know that crystallization rate, it's a pretty important parts during the 3D printing process in order to control the warping effects. And then we try another polyamide. It's an amorphous one, so called Riesland Clear. And this material is not 100% bio-based, but anyway, it works as well for additive manufacturing. And this one was chosen for the development because it's an amorphous one, so there is no crystallizations parameters to control, and should be easier to process. And then we try another candidate, definitely different from polyamide. This one, it's a high temperature, high performance polymer from the capstan family. It's a polyether ketone, something similar than PIC. And these materials get higher performance in terms of mechanical performance, but also in thermal performance, because the glass transition is pretty high, something close to 160 degrees. When you compare to polyamide, which start from for about 50 degrees up to 120 degrees for the Riesland Clear. So this material, it's a pseudo-amorphous polymer. That means it's a bit crystalline, so we have to control very well the cooling during the printing process, which could be a bit tricky. And then for all candidates, you can see a column with the expansion temperature, the CTE. It's pretty important to get this value in mind, because at very low temperature, when we will mix these organic materials with some reinforcement, we have to be careful about the choice of the reinforcement, because if they get a different CTE, it could lead to some defects, some micro cracks into the materials. And as you can see, polyamide is twice lower than PEC material. So then I will present the reinforcement used in the project. So we use different kind of reinforcement. The first one is basalt fibrous, but in short fibrous. In the picture, you can see continuous filament fibers, but in the project, we use some cuts with 6-8 millimeter lengths of fibers. These materials are get pretty high density, like a glass. It's something like close to 2.6 in density. And as you can see, the expansional thermal behavior is very lower than the polymer ones, because polymer, if you remember, it's close to 25, and here it's something like below 1. So, so that's why we made a lot of trials and measurements. Later on, you will see on that slide, just to control this behavior. Then we try another type of materials, more in powder form this time. It's a bio-based one, because it's oyster shell calcium that we plan to use in order to stabilize the polymers in terms of warping behavior for the crystalline ones. So this time the CTE is a bit higher, closer than the polymer, close to 5. And finally, we try also some nano reinforcements, like a carbon nanotube, but a multi-wall. Density are something like lower than the other ones, but still high for a carbon one. So we use the Graphistrans C100 from Arkema, and just to check if some nanofibers could enhance the mechanical resistance at very low temperature. So we made plenty of formulations at different ratio with different additive, etc. And finally, we focus on final formulations. made of polyamide 11 for the matrix, and then with short basalt fibers for the reinforcement. Because this combination of materials shows a better printability for large-scale additive manufacturing, and then show very good mechanical behavior at 20K. So the material was made in two different steps. The first one, it's what we call the compounding step. So we used as ingredient the raw material in thermoplastic pellets for the polymer, and then a bundle of short fiber, about 6-8 millimeter length for the basalt fibers. And to make them, to blend this material, we used what we call a twin screw extruder. So I'm gonna to present it to you in a short video. So here you can see the room where Canway is manufacturing all this material. So here we can see the dosing unit where we just fill each dosing unit with different material. Here it's the basalt fibers, and then you will see the pellets one. And the pellets, polymer pellets, was fed into the main feeders of the extruder, so on the right on the video. And then it's conveyed by two screw, 26 millimeter screw in diameter, and then feed in the side feeders the different fibers in order to blend them, to melt them, and then to get a good homogenization of the fiber inside the polymers. And then you can see the cooling process, and then the pelletizing process in order to produce some pellets. So obviously, in these pellets, the fibers get not anymore 80 millimeter length. It's a bit shorter because of the grinding here and the shearing of the screw. But anyway, the fiber still gets something like 0.5 to 1 millimeters length inside the polymer itself. You can see a schematic representation of this on the picture here. So then this compound was used in another tool in order to manufacture the 3D filaments. And 3D filaments is made more or less on similar process, but this time is not a twin screw extruder, it's a single screw extruder where materials will just directly feed in the main hopper and then just melt, and with a specific die with 2.8 millimeters in diameter. We just make the filament, and then we need to control the cooling at a very accurate temperature in order to get a very spherical and continuous filament. So here you can see the caterpillar pulling system, and then the spooling one, where we manufacture on conventional 3D spool the filament. So here it's about 5 kilograms of filaments that could be stored in such spool. Up here, as you can see on the picture. So if you remember well, the final object is pretty large to print, and we need to manufacture in a one shot the printing during the printing robotic process. And to do so, we cannot make some pause, some stop during the main process, impression process, because it could lead to different defects. To get you can just generate some defect during the large part production, and when you spend several hours to print something, it's a pity to just to stop it for filament changing. So that's why we developed in-house what we call a super spool, because it's a combination of several 5 kilogram spool into large one. As you can see in the next slide. Oops. Here. So doing that, we need obviously to solve different all the different small spool into continuous one. So we developed a specific high temperature soldering process, as you can see here, to to melt the filament A to the filament E, and so to get a pretty strong and unique filament. And here you get the picture of the modified spooling system using a very large one, about 35 kilograms of materials. So that permits us to print in one shot the material. So you can have here small picture when you can see all the conventional on the left bobbins spool used in 3D printing, and then a very specific one developed for OVERLEAF project in order to make a larger one. And this spool, this large spool, was then used by Ayman to manufacture the inner tank, as they will show us just next. Oops. Thank you.
Thank you. Thank you, Teddy, for your presentation. I will now give the mic to the IMEN team, and specifically to Ander, who will introduce us to large format additive manufacturing strategies.
Okay, so good morning to everyone. Thanks for being here today. And before starting with the inner tank fabrication process, let me introduce a bit more IMEN. So we are an innovation and technology center that we are located here in Spain, in Galicia. And talking about the additive manufacturing process, we mostly cover like 4 sites. We are able to work with automatic fiber placement machines or ATP. We have like the FFF process, like the one will be like the focus of today. Also, we work with metals and with concrete, and we try to cover the whole process of dance, from material development also to study their sustainability assessment, and trying to cover the rest of the steps. In OVERLEAF, here in IMEN, we are not just working in the inner tank manufacturing process. We also covering like the Orton tank manufacturing and also like the tank assembly. But today we'll just focus in the inner tank manufacturing. And well, here we have an overview of the picture of the tank, and here we have what is like the inner tank or thermoplastic inner tank. Well, as we know, the idea of this project is to store liquid nitrogen. That means that this inner tank will be in direct contact with liquid nitrogen around 26 Kelvin. Sorry. So that will put a lot of requirements into the inner tank, and that is why from the manufacturing point of view and also from the design point of view, everything will be completely designed to store that liquid nitrogens. Why to choose the thermoplastic? Well, because as Cano explained before, we have like quite good performance and materials availability. We are able to print them automatically thanks to the automatic, robotic, or printing. And we have a huge design flexibility that will allow us to make different trials and change once and again until we have like the final model that is able to provide all the requirements. Which is the biggest challenge that we have in the manufacturing process? Well, we will extrude our material around 300 Celsius, and the working temperature of the tank will be minus 250 Kelvin. Sorry, that is generating a temperature difference almost of 600 Kelvins, and that implies a lot of different things into the performance, because the behavior of the material, the shape of the material, how it performs at the extrusion temperature is completely different how it behaves at the working temperatures. So everything will be adapted, especially into the manufacturing process, to arrive to the properties and behavior we are looking for. Finally, from the transversal objectives, we have to keep in mind that this is something that is never done before, and that is carrying a lot of challenges, but all these challenges will be directly translated to the aviation industry and will allow us to gain a lot of novel knowledge. Well, and just to start before with talking about the inner tank manufacturing process, we have to understand what is like the fused fabrication, fused filament fabrication process. In this case, in where what we are doing is to the from a CAD model, we start placing like one layer, two layers, three layers, until we have a final document. Here we have like a short video of how like a very simple structure grows when it is printed, and as you can see, by stacking like consecutive layers with different shape, we reach to our final shape. Well, and as I said before, in this technology there are like several materials can be printed, but in our case we are just focusing in thermoplastics. That means that these plastics are melted and they behave viscous or semi-liquid at certain temperature. Finally, to understand our technology, we have to cover how it works. So we have like an extrusion system. It's taking like the filament that Canoe is producing, and through a filament driver, some gears, they are pushing the filament, who is melted into the heat block or the heated nozzle. And finally, through different movements, we reach to our final 3D model. Commonly, at home, the people is usually having these Cartesian or 3-axis machines in where just there are 3 axes of movement, as you can see, X, Y, and Z. However, for in our process, in where we are using like a large scale additive manufacturing, we are using roboticized arms. That means that these devices, this hardware, has 6 axes on it, as you can see, and this is increasing a lot, like the complexity and the freedom of movements that we have to build our systems. Additionally, for this project, what we are having is an extra 7 axis that is able to rotate our figure of our model. Well, what is the problematic here? That for Cartesian printers, this is like the 3-axis printers, everything is very involved. But for large-scale additive manufacturing with robotic-sized arms, the path planning versatility is quite limited, and this is bringing us like quite difficulties. Let me show you how we assess them and what we use for our path planning. Here you have an overview of the path planning software we use for this project. Is called A-Build, and as you can see here, what we are using is a simulation of our robot and a simulation of the model that will print. This model is divided in several points and will select the tool orientation, the tool speed, and the extrusion properties and everything to generate a path planning that will be a simulation or the covering all the information that will happen during our real print. The point here is that this program, even quite involved, have certain limitations, and the freedom to select and to choose what is happening in every time, in every moment, is quite difficult. Still, knowing a lot the program and doing like a lot of changes and swapping a lot of different programs, we are able to make whatever we want. Well, once we have our path planning tool, what we have to understand now is what we want to print. Here you have a model of our inner tank. As you can see here, it is divided in 2 different components. A bigger one that is like the lower inner tank, what we call the sphere. We have an upper inner tank. As you can see, it is connected to a segmented tube or a column, and both will be placed together to generate like the definitive inner tank. Here you have a couple of pictures of the inner tank or some of the components, And I will like to highlight a couple of details. First of all, this tank have a lot of details. It has like a small component on it. As you can see here, we have like just like a 5mm wall, but remember, we are printing a huge tank. It is a large scale. It's more than 100-hour print, and this is bringing us a lot of problematics. And just to make an idea of the problematics that this large-scale printing is bringing, let me show you this super short example. Here, what you are watching is a mock-up of the tank. This is like we are taking the huge tank and we are reducing and trying to print it. Here you can see that we make a reduction of 10:1, so we are just printing like 0.5mm thick walls. We are having like 0.1mm layer height, and we are using like the same printing conditions, around 300 degrees Celsius into the extruder, a chamber at 80 degrees Celsius, and a printing speed of 50 meters per second. Well, this sphere, it takes us around 2 hours of focus work just to design, to make the path planning, and to print it, remember, in Cartesian mode. This is like just with 3 axes. It took like around 10 hours of print and just consumed 15 grams of material. It was super easy. Well, here you have a comparison between our mockup, a real person, and the inner tank. It's huge. And this is bringing us like a lot of problematics, not just from the path planning point of view, but it's bringing a lot of problematics because it's a high performance tank. It must to cover like the liquid hydrogen on it, and it must to be like with the shape that is designed, because the design, as other colleagues will explain later, is quite important. So, well, among all the different problematics that is bringing, let me highlight one: chamber temperature. How are we able to increase the temperature to have a correct printing process? That is quite difficult. Imagine if we just having like 1.5 meters diameter tank, imagine how the room it is. So the room is more than, I don't know, 20 square meters, and it's very difficult to heat it up. Besides, we have an isotropic printing process. What this means? That remember, we are stacking one layer in top of the other, and that is generating completely 2 different axes. In one side, we have a set axis in where different layers and are stacked between them and generating an interface. This is not continuous. However, if we watch from the top view, what we print is a completely continuous phase. And if we remember Carnot stock, we are having inside our material fibrillar materials, which are usually aligned along the x-axis. That is generating completely 2 different behaviors in our materials. Besides, on top of it, we are printing at very high temperatures because we are printing melted materials. But into the bottom of the tank, it will be completely cold. So this is generating an extra problematic. What we do for that? As we'll see later, we are making testing coupons to understand the behavior in both sides, but from the hardware point of view, from the point of view of manufacturing, we have to make able to homogenize and make as isotropic as possible our materials. How we did this? Through a heating system. In large-scale manufacturing, in general, in 3D printing, there are several heating systems, as you can see, like heater, laser system, LIDs, or IRs, infrareds. This is the system that we choose for the inner tank manufacturing. For that, what we did, as you can see here into the top view, we are watching like the tank from the top. What we placed were like several IR lamps that are heating like the tank from every side. This is allowing us to increase the temperature of the whole tank without heating the whole environment. And it is more simple, and we can reach it. Besides, we have like a IR lamp into the printhead. This allows us to increase the temperature of the top surface, and in this way increase the adhesion between layers, in this way making the whole structure less isotropic. Here what you can see are few pictures of the setup, and you are watching the tank is fully covered by IR lamps. Here we have our printhead with an extra IR lamp directly hitting into the top surface of the tank, and here we have an ER image of what is happening. You can see here in the top is almost cold. Here we have an interfacing where the tank is warm, and at the end, into the top, we are increasing a lot the temperature to improve as much as possible the adhesion between layers. Well, let's continue and go a bit faster, sorry. For tank design, we also have to cover like the different subcomponents that are making the tank itself. This is a huge tank, and there are a lot of different components. Here I will show you just a couple of examples, because we don't have too much time, about the process we perform. For example, for the button, we require some specific thickness, but because different printing parameters and the path planning, sometimes some errors ahead. So what we did to modify this to reach like a completely homogeneous and flat surface. Here you have another example about a cross-section of our materials and how we improve the printing process to remove all the errors, to all the defects, and reach a perfectly compact and defect-free structure. And just to finish with the subcomponent trials, here you have an example of how we run different steps to, first of all, design like the adhesion size between the column and the inner tank, then print the whole column, and finally we printed like the inner tank a small component itself. However, we have a small problem. It's always impossible to print the reality. Why? This is a super stupid and simple example. If we have a huge tank, we'll never be able to print the top part, because yes, maybe we can cut the tank and print the sides, but how we know the ear lamps hitting the tank will have an effect on it? Well, so that is impossible. So this is why it's super important, like the monitoring and control. In these pictures, what you can see is the exact moment when we are printing our tank, how we are watching the whole process by optical cameras with IR lamps. We are controlling like the extrusion process itself. And here you can see a couple of images, one about how the column watch while it is printing, and then like the IR lamp, the IR camera, how is covering the temperature to be sure that we are reaching like the higher printing temperature, and of course we are having almost isotropic or the most isotropic properties that we can reach. Finally, sometimes the control is impossible. Sometimes things happen are not okay, and that is why we have to repair the defects that they happen during the printing. Here I showcase a couple of examples of how we worked into the start-stop option. This is, we have an error, we stop printing, and then we start printing again, but before I start printing, we increase the temperature of the whole surface to improve the adhesion between layers. And here we have another example in where we make a couple of holes just to see the repairability of our structure. The video you're watching right now is a heat gun in where we are placing like some material, some cold material. It is getting heated and is covering the hole that we made before. In this way, we are reaching to a completely prepared surface. And just to finish, let me show you like a few pictures of the tank, how it was printed. You can see here that it is huge. Actually, in the picture looks smaller than what it is. And here just a couple of pictures about the other part. And to finish, let me thank the both guys that they are the main guys of this project, Xavier Perez Ferrero and Manuel Montero. these two guys made the whole work, and a video that is getting frozen, a bit frozen, about like the inner tank printing process and how it looks from outside. And thank you very much.
Thank you, Ander, for the presentation and in respect to the time. So thank you for that as well. Now I will leave the floor to Jordi Renard from University of Girona, who will introduce us to mechanical testing of 3D printed materials at cryogenic temperature for the design of our tank. I will now give the control of the presentation to Jordi and let you speak. You should now have the control.
Okay, thank you, Leonardo, for
Thank
the
you.
introduction. First of all, let me introduce the team who has been working on this part of the project, who are Quirze Abella, Albert Turon, and Jose Manuel Guerrero, all of them from the AMADE Research Group from the University of Girona. So in the OVERLEAF project, our objective was related to the design and also to the mechanical testing of the materials. In the previous two presentations, we have seen which material was chosen for this project and how it was printed, let's say the design, no? the final design. But to reach this final design, so we need to know the properties of our material. So I will start with the same slide like my colleagues. So with the tank. In this tank, so we have let's say the inner vessel, the outer vessel, and here in blue, the isolating foams. But in that case, we focus our work on the inner part. From a mechanical point of view, our point of interest is that this inner tank has to storage liquid hydrogen at 20 Kelvin. There will be thermal stresses, stresses induced by the change in temperature, as Ander has very well explained. Also, the material is done by additive manufacturing, 3D printed material, as we have seen before, with a thermoplastic resin, the polyamide 11 plus reinforced with a basal fiber. So in that case, from this data, we can say that if we want to design properly the inner tank, we need to know the properties at 20 K. Also, for us, it is important to know the coefficients of thermal expansion, because we have seen that the material behave different in the two directions. So we have an orthotropic material, and of course, apart from the strength, we need to prevent leakage. These are let's say, the motivation of our test. But of course, the first idea, since these are new materials, is to go from the properties to the final design. But we cannot do it in a straightforward manner, but we have to follow this building block approach. So we will start initially from the material characterization, characterizing coupons and performing mechanical and thermal tests. We have realized that we need intermediate test. We have called element test with T and disc specimens. We will see these dimensions later. And it is also interesting to do a small test with a test with a 3D small vessel. All in this case, all the specimens were manufactured by Aymen. Now, to reach, at the end, we want to reach the design of the final tank, but we need to pass through these all phases. How, apart from that, apart from the test, we will also complement our information with finite element simulations at different levels. So how we will proceed with that? So we will follow this, let's say, this scheme. So first of all, we have the material characterization, or we determine the properties of our printed materials. We will perform a design of the whole tank, and this design will be complemented by testing of the intermediate levels, element and subsystem, complemented with finite element analysis of these elements for a final design validation. Here we will focus on the testing part, but we must know that since these intermediate elements are complex, so we need also to perform finite element for these intermediate elements. So let's start with the first step of this pyramid, that are the material characterization campaign, and we will focus on the mechanical test. Here, to not get lost, so we have on the right side the pyramid and the different levels of this pyramid. So for the mechanical properties, the main objective is to know the properties at these low temperatures, at 20 Kelvin, and for this, we have developed an in-house cryostat that is capable to reach down to 10 Kelvin, so we can reach from a room temperature to 20 Kelvin. This cryostat is attached to a universal testing machine. It has some advantage from other designs that uses, here we can see in the picture, that uses cryo coolers, in which we can save a lot of liquid helium. In that case of testing in a hydrogen environment, for safety reasons, we are testing in a helium environment. The current equipment, the testing chamber is quite big. It's 250 millimeters per 200 millimeters in diameter. At that moment, it's prepared for tensile test, but we plan in the future to perform other tests, like the tests that typically are done at room temperature. In that case, the specimens tested were dog bone specimens. We follow this standard, so thanks to the dimensions of the cryostat, we could test the standard specimens. And as Ander commented, so we have tested two different directions. One is the printing direction, or a specimens printed in the printing direction, and another set of specimens perpendicular to the printing direction to know the properties in both directions. There is a third direction, Y direction, but in that case it was considered that had the same properties than in the Z, that is perpendicular to the printing direction. From this test, we obtained some preliminary results. Here I have normalized with respect to the longitudinal modules in the printing direction. Here we have a graph with two columns. On the x-axis, we have the temperatures. On the y-axis, we have the normalized mechanical properties. And in blue, we have the longitudinal properties according to the printing direction. In orange, perpendicular to the printing direction. All these results are normalized with respect to E11 at room temperature. From the results, we can see that the modulus increases at 20 K, so this is good for this more stiff, let's say, the vessel. But we have a huge difference in the properties in the printing direction and perpendicular to the printing direction. So if we look at room temperatures, we can see that the transversal modulus is 50% of the longitudinal one. So this can affect to the design, because in this kind, this vessel will be orthotropic. So this is why we have modified, and we don't have a pure, let's say, spherical. So we have this has had an influence on the results. On the other hand, we have the strength and ultimate stresses. So F1 or F are the stresses, E are the strains, 1 is printing direction, 2 is the perpendicular to the printing direction. Again, we have the two temperatures and the normalized mechanical properties with respect to the stresses at room temperature in the longitudinal direction and strains here in green at room temperature with respect to the longitudinal direction. Here we can see that the tensile strength increases as we go down. The maximum strain decreases, so the matrix becomes more brittle when tested at 20K. So we have to take this into account in our analysis. Also, at the base of our pyramid, we have performed a characterization of the void content. So we have used 3 different methods. 2 typical methods, acid digestion and calcination, according to the standard. But since we first tested materials without reinforcements, and since Canoe has shown in this presentation that we have used some materials with organic fibers, if we use acid digestion or calcination, we can damage these fibers. So we have used a third alternative method, that is scanning electron microscopy. So taking pictures of the site or in the middle of the specimen to detect voids or to detect the quantity of fibers. All these studies also have been complemented with with microcompute tomography. In that case, we have an equipment that with an X-ray source and a detector. Here on the right side, you have more or less the main properties: voltage, intensity, power, and the size of the detector. And we use this equipment for porosity content and fiber orientation detection. So here I have a couple of images for the thermoplastic resin plus basal fibers in which we detect the porosity. Here you can see in black small holes. And on the right side, if it loads, so here we can see the fibers. So we can detect, for example, the percentage of fibers oriented at 0 degrees or according to the printing direction, apart from knowing the percentage of the fibers. And finally, we have characterized the thermal expansion coefficient by 2 methods with the push rod dilatometer. That it's a typical equipment, but also this equipment is limited to this range of temperatures, minus 160 degrees to 40 degrees. So we have performed additional measurements with the strain gauges while cooling down our specimens. On the right side, here we have a couple of graphs with the thermal expansion coefficients with respect to the direction of with respect to the printing direction, and also perpendicular to the printing direction, with a dilatometer that ends at this point, and with the strain gauges so we can reach lower temperatures. We can see that this thermal expansion coefficient is not constant for this material. It's almost, it's more or less constant in the printing direction, as Canoe showed, but perpendicular is not. So we have to take this into account in our analysis. At this point, we have reached or we have completed all the tests at the first level of the pyramid. Now, if we move to the second level with the element level analysis, when we deal with an orthotropic material, we can have as we will go down to 20K, so we will have some thermal effects. Specifically 3. The first one is abrupt changes on printing directions. Imagine that you want to print and you want to reinforcement certain regions, so you have to take care because you will have a printing direction with a base circumferential, but the reinforcements can be radial. So here there will be thermal stresses. A second point is that if we have zones too thick or thick zones, maybe we can have infills at printed at plus minus 45 degrees. So this means different orientations and different thermal stresses. And the third point is that even if we print at a circumferential printing, so we will have different thermal expansion coefficients. So there are certain zones, for example, this is a central part, that can have a higher stresses. We have tried to simulate this in the whole tank, but we have found that finite elements fails to capture the behavior of these structures or these singular points. So we have to design several elements to try to analyze these singular points and support this analysis with finite elements. And this is what we have done in this project. So with Aymen Asiturri, we designed two different element level tests. One was a T specimen. This is this figure on the right top that tried to simulate the change in the printing direction when you have a reinforcement. And we had another that was another specimen that was a disc specimen that the objective was to simulate a 3D printing in field or circumferential printing. All these specimens were instrumented with the strain gauges and thermocouple and put at 20 K and at different thermal conditions to see the damage and to get the response of these materials to see if there was failure or there wasn't. Finally, for the third level of the pyramid, that was the subsystem level testing, Aymen manufactured a small vessel that was tested in our installations. And what we first did was we performed a thermal cycle to 20 K to see if with this thermal cycle we created some damage on the matrix. Then we performed a thermal shock and a leak test, and finally a water tightness test. The objective was to check different singular points and to see if there was tightness of this vessel. This vessel was monitored with strain gauges at different locations, on the top, middle, and at the bottom of the specimen, plus with thermocouples during all the three phases to check if there were leakage of liquid nitrogen. This is for safety purposes. This is an open vessel, so here the liquid nitrogen can get out, no? And here we don't have an increase, a dramatic increase of the pressure. This is more or less an overview of all the tests that we have performed. Here are some conclusions that we have found so far in the project. So it is feasible to use advanced materials for liquid hydrogen storage. We have seen in the previous presentations how we can manufacture, how we can create them or develop them, how we can manufacture, how we can test, and how we can design with them. But we have to take, in the point of testing, we have to take some considerations. The first, the autotopy of the material that can induce material stresses because of these thermal loads. So the finite element simulations, at that moment, at least our simulations are failing to capture the behavior of this 3D printed material. So we have to create, target, develop new singular geometries to try to capture these singularities. Only to finish here, I have to say that inside, well, this work has been performed by the research group AMADE from the University of Girona. And just here you have the QR code, just if you want to take a picture and go to the web page of the research group. Thank you very much for your attention.
Thank you very much, Jordi. Thank you for your presentation. Thanks a lot. I just wanted to say to the audience, for those who join later, that you can write in the chat all the questions that may arise during the presentations of our speaker, and we will address them at the end. But with no further ado, we'll now lead the floor to the ICSI team, specifically to Eusebio Larian, who will talk about removal of trapped gases from open cell forms for use in hydrogen cryogenic environments. I will now give the control to Eusebio. So please, Eusebio, it's your turn.
Thank you very much. For a team from National Research Institute for Cryogenics and Isotopic Technologies, I will present part of our work that we perform on this project. And I will focus especially on the removal of trapped gases from the open cell forms, specially designed for use in hydrogen cryogenic environments. I put my presentation in a few parts, especially a short presentation of open cell foam samples, how they look like physically. The second part, it's about the moisture removal from these open cell foams by the process of desiccation. The next one is the removal of moisture, especially water, by lyophilization process. And the third one is related to the removal of oxygen on this situation by dry vacuuming. I just want to pinpoint that due to the specific of our project, due to the specificity itself, to the volume, due to the materials that we use, high vacuum was not an option. So we need to focus our attention on different methods to eliminate this moisture and especially the oxygen. As you know, open cell foam is used as a very good insulation material, and due to the specific design of the vessel itself, it was mandatory for us to take not only the moisture out from the system, but also the oxygen. In some specific part of the vessel, hydrogen is in close contact with open cell foam, and the elimination of oxygen, it is mandatory due to the effect that ice of oxygen is got on the hydrogen, liquid hydrogen. We try to take this water and oxygen out from the samples from using different approach. First of all, I will present short, fast, the water removal with laboratory desiccators, also with lyophilization equipment, and later on an oxygen removal experimental rig necessary to eliminate oxygen, but down to very safe levels of oxygen, but only by using low vacuum. Jesus Christ. Okay. Now our samples look like in the right due to the numbers of the samples that we use. We try to cut them almost on the same shape and round, like small cylinders. And this is an example of 5 of them. Samples with which we perform our testing. In the left, you have the weight of the samples initially, and after 24 hours, a mass decrease from the desiccator. Please notice that this desiccator was with a kind of moisture trapping material, and this is current practice when we try to eliminate moisture from different materials. It is not the best. It is just a conventional use. It's very well used practice in this cryogenic field. On the column on the right, you have we present like a percentage mass decrease from these samples. It can be seen that for this particular material, the values were around 5%. And something is wrong. I don't know. Anyway, Here, I missed one. Here we have the results in after 72 hours in desiccator, and also the weight percentage, the weight evolution after 24 hours in air. What do I mean by that? We try to figure out if these samples after water elimination will be capable of extracting back humidity from the lab atmosphere. And indeed, we figure out that after 72 hours in desiccator, the samples that we test were capable of being in a dry situation, but by taking them out from the desiccator in 24 hours, they have the tendency of retaining back humidity from atmosphere. So it means in the real working conditions, after somebody will perform this desiccation process, he needs to make sure the samples or the vessel itself, it's sealed off, because it will catch back the same amount of humidity or something close to. In these two graphs, we present water content evolution after 120 hours as mass, and also as a percentage of a mass. From the graph, you can see that the vast majority of the water is eliminated in 24 hours from the desiccator, and after 72 hours, if we keep the samples still in a desiccator, the mass and the percentage is not the variation is not very significant. It means 24 hours can be enough to take the water out, although if the samples will be put back into the lab atmosphere, will catch back the same percentage of water, almost to the same levels. As a short conclusion for this step, can be seen that moisture loss in 24 hours is significant. It's close to 5%, which means the samples that we investigate were not soaked with water, but have a large content of water. After 72 hours in desiccator, the moisture was still recorded or still there, and when re-exposed in lab atmosphere for 24 hours, the samples were capable of trapping water from the environment. So as a next steps, we decided to use a lyophilization process in order to observe if even after 72 hours in desiccator the moisture is still present or the moisture can be eliminated. And in the same time, we figure out that oxygen removal test must be performed in order to determine if after the water elimination, oxygen is still trapped into the material by different physical properties, such as bonding or because of the trapping properties of the material. Here we have some samples as we prepare them before putting them onto the lyophilizator system, lyophilizator tubes. We try to keep the same type of numbering, and also we try to keep the same material. So as the steps, the samples were initially weighted to see to have good values, and after that were continuously kept into the vacuum freeze dry lyophilizator for 24 hours. And on the bottom right, you have an image of the samples into the liquid nitrogen bath, which was part of our lyophilizator. As samples, as real values for this, you can see that in 2 hours we recorded, because I presented here in 2 hours, after 2 hours, after 24 hours, and the third step, it is after 1 hour back into the desiccator. Why we did this? Because the results are very interesting. Lyophilization, it's a process with better efficiency of water extraction. So after when we keep our samples in lyophilizator and we put them back into the desiccator, actually the samples extracted humidity from the desiccator itself. It was a very interesting phenomena, and this gives us an idea that the lyophilization process is faster and more efficient than usual desiccation. Here we have the image of a graph of the results, and also the time evolution after 24 hours in lyophilizator and after 1 hour in desiccator. The negative part of the evolution is due to the fact that the samples were extracting humidity from the desiccator molar sieve itself. It means they were from the lyophilizator. They were so dry. So as a note, some short notes regarding this step. It can be seen that the foam samples can retain moisture at any time when exposed to air. That the lyophilization process, it's good. It's not really fast, but it's very effective. And as a next step, as an observation, oxygen removal test must be performed to determine the oxygen content of the samples and to see if the material still have bonding trapping properties even when the material is in very dry situation. This is an image of our oxygen removal rig, experimental rig, with samples inside of a kind of vacuum chamber with some bottles of helium and with a dry vacuum skid capable of extracting gases that are in an oxygen removal rig. Our idea was to see if any oxygen it is still present into the open cell foam after the foam is dry, but especially to see if by purging or by keeping at a small vacuum, the complete oxygen can be removed total. As I said, the idea was to eliminate water, oxygen, water also, just by purging or by using small vacuum, small value, 10 to minus 10.2 at 10 to minus 1 millibars. It is not a very, it's a rough vacuum, is not a very strong vacuum. The analysis that we perform with a gas chromatograph, and here we present the oxygen content after a few cycles. Initially with the atmosphere, after a few cleaning cycles, and after the first cycle, second, third, fourth, it can be noticed that the oxygen content can be lowered to values that are considered as being safe for working with liquid hydrogen. So no less than 5 cycles of rough vacuuming are recommended, and also as a safety precaution, and the gas chromatograph can be used to actually verify the real content. We have an example of a gas chromatograph that was taken in one moment in time, and this is an image of the last gas chromatograph with a very low oxygen content. I present here the sharp evolution of oxygen content. It can be seen that after, in the last cycles, the evolution is not very fast. So cautions, additional measures shall be taken in order to make sure the value reaches safety safety levels. Regarding the oxygen content removal by the dry vacuuming and by rough vacuuming method, we need to pinpoint the limitations, especially the value of the vacuum, 10 to minus 1 millibars. It can be seen that the evolution of oxygen content does show a good factor of its removal, especially for this type of the forms of materials, insulation forms. It means at this value, the oxygen is not the forces that keep the oxygen into the structure are not very strong. Also can be noticed that the foam samples can be depleted of oxygen by vacuum down by this value of vacuum down to values below 2 ppm of oxygen. As conclusions, moisture depletion from the samples can be performed using desiccation or lyophilization methods. For the removal, it was well known that for the removal of oxygen, dry rough vacuum is an effective method with some limitations due to the specific of our project. But everybody must be very careful because these materials have the tendency to return to their initial values, especially for the humidity, and this can be a very strong limitation for some applications. So basically, all is new and all is old. Thank you very much, and sorry for I don't know what happened to my computer. I try to rush a little bit to
No worries,
stay on.
Eusebio. You did
Thank
it
you.
actually. So thank you.
Thank
We
you.
still have 5 minutes for Q&A. We'll stop sharing so that we can see each other properly. Okay, I will now read the question that we have in the chat, and I will invite everybody to write them down if they have now. The first one that I can see, it says like that. So you guys, congratulations first. So you guys are closing the gap between prototyping using 3D printing and large-scale manufacturing. Not only this, but also to fix the common problems of 3D printing, like the isotropy, fixing a layer during the printing process, or even welding filaments to have one smooth printing process with no filament chase, thus no layer shifts. For technology's sake and to advance in this field, this is very innovative and great, but for the project scope, is there no other way or approach to build a tank without the 3D printing technology? I think this is a question for the EMEAN team, or for everybody. It's open. I mean, but I will invite Ander first to reply, and then the others they want to jump in.
Okay, so the answer is yes, of course. I mean, I think that in industry there are a bunch of different available options, and just exploring all them will know which one is the best for each application. We have to remember that this is something exploratory. That means that we are changing almost every day our idea. We are exploring new options, and this is something that just the additive manufacturing provides. So this versatility, this adaptability. So even I think that different manufacturing options will be at the end better. How to explain this? Like, let's imagine that we have like a final model, everything is refined, we have the final material, we have all the components well defined. Probably other technologies may make it easier, at least. Just let's call it like this, easier, because additive manufacturing is still young. It's a young technology. That means that we still have to learn and develop many things to reach the other technologies, how to say, like the quality. But from in one side, I think that the additive manufacturing is good for versatility. In the other side, other technologies will be probably better. So let's say it like this.
Okay, thank you, Ander, for the reply. I don't know if the camera team want to add something on that, or Jordi, or or if it's it's everything. Yes, go ahead.
Yes, if you want, I only add a small comment that it's that in terms of the testing on the design, all the developments that we have obtained can be applied to other materials, let's say other more widely used technologies and materials. So these are also valid.
Okay, thanks, Jordi, for complimenting. I can see that there are no other questions in the chat. There's Falau is thanking us for replying. Thank you. I think that we're also running out of time. Therefore, I would like to first thanks all the speakers for presenting the OVERLEAF developments and results today. Thank you all. And I would also like all the attendees for attending. We will upload this webinar on our YouTube channel, meaning that if you want to review everything that we said today, you can do that. So make sure to follow us on YouTube as well. And yes, with nothing else to add, thank you all, and have a good day.
Thank you, Leonardo. Thank you, everybody.
Thank you, everybody.